Welcome, everybody. My name is Magdalena Pasciali. I am a postdoc here at Stanford working on computational neuroimaging and developing machine learning models to enhance understanding of neuropsychiatric disorders. Today, we have a very, very interesting session titled Key AI Advances for Improved Understanding of Diseases. And the session has 4 experts that will give 15-minute talks. We have Sharmila Mazumdar from UCSF. We have Renee Yao from NVIDIA, John Long from Stanford, and Exana Deli from Stanford. I think in the beginning, we will start with the 15-minute talks, and then afterwards, we'll have a 30-minute panel discussion. I encourage all of you to engage with us and send us questions. You can send in your questions by hitting the engage button. Then you will be linked to the Slido website where you can ask a question. And then during the panel discussion, I will read your questions to our speakers, and then we can have a very interesting conversation. Feel free to address them to one speaker directly or in general to the panel for the discussion. So our first speaker for this session is Professor Sharmila Mazumdar, and she will talk about key AI advances, and we'll talk about an example of osteoarthritis. So I would like to give the floor to Professor Mazumdar. Thank you so much for your talk.
Thank you so much. I'm going to start with sharing my screen, obviously, and I'm delighted to be here. Thank you for inviting me. And I very much look forward to hearing the rest of the talks and engaging with the audience in this very exciting seminar. So as you heard, the topic is Key AI Advances for Improved Understanding of Diseases. It is a very broad topic, and I could talk about each of the key components with AI, the advances, diseases, what is understanding. However, what I thought I would do is I would highlight what has been happening in this field using the disease of osteoarthritis. Why do I pick osteoarthritis? It's a degenerative joint disease and a leading cause of disability in the United States. The prevalence is extremely high, and while people thought it was a disease of the elderly and the aging, as a result of trauma and injury to the joints, this has become a reality for many people who undergo knee replacements even at the early age of 40. So given this, why am I picking osteoarthritis when I could have picked diseases which seem far more scary, difficult, morbid, like cancer or heart disease? Well, once we've cured cancer and heart disease and we're living for 100 years, what would life be like if we were immobile and our joints were not working and we were unable to do the daily things that we needed to do? The musculoskeletal system is extremely important for the growing population that is aging, as well as the younger population who seems to be having degenerative joint disease very early on. The contributors to knee pain, for example, a site of osteoarthritis, or hip pain, are very poorly understood. There are clear factors associated with demographics and economic factors and gender and race issues which contribute to osteoarthritis, but it is measured, pain is typically measured using pain-reported outcomes, which are extremely subjective, and it is typically assessed using radiographs by looking at the space between the 2 joints in the knee. In fact, this is the only thing the FDA actually approves of. Magnetic resonance imaging is a modality that shows you the soft tissue of the joints very clearly, as shown in this particular set of images at the bottom right here. You can see the cartilage, you can see the meniscus, you can see what is happening in the bone, whether there's basically inflammatory signals or bone marrow edema-like lesions. You can see synovitis, which is again another inflammatory response in knee osteoarthritis. But this methodology has not been adapted for osteoarthritis assessment for unapproved by the FDA, despite its superior soft tissue contrast that you see. And I'll tell you the reasons why this is so. So laying the groundwork for osteoarthritis, let's talk about the x-rays. These are x-rays showing the femur and the tibia for those of you who are not used to seeing x-rays, and you see little outcroppings of bone called osteophytes, and the distance between these two bones actually narrow. And sometimes you see these images in an airline magazine saying how you can improve the joint space. So typically this is graded using a grade called Kellgren-Lawrence scale grade. This basically is, again, a subjective grade which radiologists actually use and grade it. There's a lot of heterogeneity and variability depending on who the radiologist is. So CNN and convolution neural networks have actually been trained that can actually quantify Kellgren-Lawrence scales from radiographs, and they perform very well. There are multiples of these, and this has been a great AI model that has been deployed. It has good agreement, good kappa values, and this is in comparison to the agreement between two radiologists. But when bone changes occur in osteoarthritis, it is rather late. So what one wants to do is actually have similar grades from MR images such as this actually derived using AI algorithms too. This has actually also been done. Various tissues of the knee, such as the cartilage and the lesions in the cartilage, have been graded using AI algorithms. Models have been developed, tested, and validated. And this is just an example, this particular graph, which shows you the performance of the DL model for predicting normal cartilage, partial lesion, and full lesion. And in these columns, you see the agreements between different radiologists. If you actually look across the numbers, you actually see the deep learning models predict these kinds of lesions from MRI images almost as well as the radiologists, and in some cases better than the agreement between two radiologists. Why is this important? This is important because one could actually use these grades derived from the artificial intelligence algorithms to standardize the grading between radiologists, improve the grading between radiologists, and actually bring the time down for looking through stacks and stacks of thousands of images down considerably by knowing where to look. If you know and you're guided that the cartilage is normal, then in which case you probably don't want to be looking at it for too long. So I want to talk about one such grading system that we have developed, and the question we asked, can we automate or assist radiologists in MRI readings? The problem gets even more complex. The knee joint has different compartments associated with the different bones, the different sides of the body, such as the medial and the lateral compartments. Besides the cartilage, there are other tissues, the meniscus, the bone, the ligaments, and basically an algorithm trained to identify abnormalities in this system in the whole joint spits out 60 probabilities. How do you present this to the radiologist? So we've come up with this report format. Green is normal, moderate is yellow, and severe lesions are in red. And we wanted to check whether this particular model with a multi-class sensitivity ranging from 70 to 89% for cartilage, for example, and varying between meniscus, bone, and ligaments was comparable to the reading between radiologists. So there was a study which was done where 50 clinical MR cases were graded by a senior radiologist and 2 trainees. If you look at the agreement between the trainee and the radiologist, it is pretty low. The weighted kappa is about 0.4. After a washout period, the trainees were provided the algorithmic output, and then they regraded the images, and you can see that the agreement between the attending and the trainee improved. So this could be a teaching tool, it could be a standardization tool, and so it brought reduced time as well as probably improved grading in the disease of osteoarthritis. Ultimately, in osteoarthritis, the outcome is total knee replacement. This is where I start introducing the big data set called the Osteoarthritis Initiative, which was approximately a 5,000 patient study over a period of 10 years, where patients essentially either had or were at a risk of having osteoarthritis, and they either progressed or stayed steady. Some had knee replacements during this tenure of 10 years. but all of the patients were well calibrated, well characterized. Everything was collected, including radiographs and magnetic resonance images. Magnetic resonance images not only showed the joint soft tissue, but it also provided information about cartilage biochemistry in the form of T2 measurements. Using this data set, we trained an algorithm to determine patients, to actually predict who would have a total knee replacement within 5 years. And the input was the magnetic resonance images, the clinical demographic factors. And what we found that the algorithm actually predicted who would have a total knee replacement, even though many of the subjects who actually had total knee replacements were not in the osteoarthritis cohort. They were considered to be in the control cohort when one looked at their radiographs. This was a significant step in that you could predict 5 years ahead of time who would undergo essentially a total knee replacement. So AI has enabled us, of course, to do automatic tissue segmentation across all organs and different organs. In the knee especially, it has enabled the segmentation of cartilage, bone, and meniscus, and using, as well as muscle, of course. And by using some of these segmentations, it is actually possible to get a feature space which describes the whole joint more completely than a radiologist would do in clinic. So what is this whole joint feature space that we are talking about? So if you take the MR images in the osteoarthritis initiative, you can segment the cartilage and determine the thickness of the cartilage across all compartments of the knee. You can look at the shape of the bone. And as I said, this data set also contains biochemical information of the cartilage in the form of T2. You can get all of this information, including the meniscus shape and features, and you could essentially reduce the dimensionality using 3D Disney and get Euclidean distances, distance matrices, and determine the similarity between individuals within this space of 100 modes derived from each of these metrics. So what you're doing is essentially using AI to basically decompose the images into its different tissues, extract the parameters, create a principal component space, reduce its dimensionality, and look at similarities within this particular space. If you look at people who are identical with their imaging characteristics in this space, they are imaging twins. What are the features that sets people apart who are controls and those who progress? Let's define who are the controls. The controls are people who had Kellgren-Lawrence scales of 0 and 1 throughout the entire osteoarthritis study across the entire duration of the study. So they had no features of radiographic osteoarthritis. But then you have the incidence cohort, which is approximately 357 subjects who essentially had Kellgren-Lawrence scores of 0 or 1 when they started, but subsequently went over the 8-year period to a Kellgren-Lawrence scale, which was greater than 1. So they progressed in their osteoarthritic status. But when you actually looked at people who were imaging twins, but what are the features that separates essentially the imaging twins who were controls versus those who progressed? One of them was weight and body mass index. This is known that body mass index is a huge risk factor for osteoarthritis and progression. The other factors were associated with creakiness of the joint. They were associated with some of the pain and the symptomatic features that the patients reported in the questionnaires that they answered. Perhaps the most interesting thing is if the people were clinical twins, if they were identical by way of their body mass index and other characteristics, were there signatures within the MR images that we could extract? And yes, we found there were several signatures related to cartilage thickness, cartilage T2, and meniscus, for example. And basically looking at which of these principal components were important, the radiologists looked at those principal components using a web-based application and basically characterized them as, for example, focal increase and decrease in the maximum lateral surface in a particular region of the knee, in the cartilage thickness. So each of these principal components have been decoded into what they mean in the characteristics of the anatomy, and one finds there are several which show differences between those who were controls and those who progressed. For example, the meniscus components, cartilage T2, which are early biochemical changes, and cartilage thickness. This level of dissection of an MR image to look at differences between people who ultimately will progress in terms of osteoarthritis is not possible today in clinical radiology. AI makes it possible. Before I go into anything else, I just want to say I'm not just talking only about osteoarthritis. There are other diseases which also benefit from large data sets and similar analysis. The ADNI data set and Alzheimer's had FDG PET images of the brain. Researchers have trained algorithms which actually predict, using the initial images, PET images, those who will actually have a final diagnosis of Alzheimer's. And so these are the kinds of things that enable us to understand diseases better using artificial intelligence. And this is what paints a most exciting future. And with all those people that I showed you and helped put this talk together, I would like to thank you for your attention.
Thank you so much, Professor Mazumdar, for your talk. Indeed, very, very interesting. And I'm excited already for the questions and the discussions. Let's move on to our next speaker, Renee Yao from NVIDIA, who will talk to us about the future of healthcare AI startups.
Can you hear me okay?
Yes, we can hear you and see you and your slides.
Perfect, thank you. Great to meet you all. My name is Renee Yao, and I lead global healthcare AI startups at NVIDIA. And great to be here and to share a little bit of insights about what we are seeing in the market. First of all is to demystify who NVIDIA is. Many audience member, you probably think NVIDIA is a gaming company. Why are we in healthcare? If you think we're a gaming company or a GPU chip company, you're focused on the bottom left circle right here. In fact, NVIDIA is a 4-layer cake, 1, 2, 3, 4 company. We have our chips that build into systems, servers, or data centers, and a whole layer of accelerated computing layer to the platform layer, to the 4th layer of AI application framework, where we have domain-specific application framework to help solve various different problems. Today, I'll be focusing on healthcare, where NVIDIA Clara is an open source medical imaging or medical devices, genomics, and drug discovery domain-specific framework that we serve many different markets in the healthcare and life sciences industry. Within Clara, you will find Monai for medical imaging, Flare for federated learning, Holoscan for streaming data, video analytics, Parabricks for secondary analysis in genomics, and BioNeMo for large language models for biology and chemistry that runs on top of our previously referred 3rd layer of the platform layer. For this, you can see that a lot of the world leading cancer center is building their AI centers with us. For example, the MD Anderson are doing AI for pancreatic cancer early detection, St. Jude's Children's Hospital, AI for proton beam therapy, German Cancer Center, biomedical imaging processing framework for segmentation and detection, Memorial Sloan Cancer Center doing AI for digital pathology and machine learning for breast cancer patient screening, and many more. For me, because I have the luxury of working with 1,800 healthcare AI startups globally, we're seeing many interesting trends that's happening in this space. From the imaging perspective, what I mean is by radiology, pathology, maybe even some of the enterprise imaging and surgery data, we see a lot more increased regulatory approval for AI accelerated imaging solutions, and a lot more of them are deploying across the globe. VizAI, AI Doc are deployed over thousands of hospitals. AZ Med at RSNA last week shared with us that they deploy over 600 hospitals. AI in radiology is becoming very prevalent. Medical instruments is becoming more and more software defined. A lot more that's happening at the edge, become more portable, and real-time streaming use cases happening at the edge in real time is becoming a reality. In medical metaverse space, we are seeing a lot more of them are coming in to build digital twins to be able to increase operational efficiency in this space. From the genomics perspective, we're seeing a lot of next-gen sequencer and be able to, with the sequencing costs going down, we were able to find a lot more insights in protein analysis using a lot of large language models. And last but not least, in drug discovery space, a lot more techniques started using AI to be able to define drug candidates and have lots of breakthrough. In silico medicine, earlier this year, have gone through human trial using AI identifying one of the first few drug candidates and many more in this space. As you can imagine, working with 1,900 healthcare AI startups here, every single one of these components can be dedicated for talks that can go on for hours. So today I will pick a very specific area, which is in imaging, and further hone in on pathology, as it is an up and coming emerging field that not everyone knows about the latest advancement, and I will share a few things in that space. So just in case the broad audience here doesn't know the current trend in the imaging space, imaging is very essential for healthcare. There's about 2 million devices, 1,600 some companies, and 10,000 modalities. NVIDIA played a role in 2D screening to 3D, 4D diagnosis to 5D treatment. Anything that you see on the map here, we played a key role through the last 2 decades around the globe. One of the very exciting thing in the imaging space is actually MONAI, and this is open source, contributing by Stanford, King's College London, Mayo Clinic, and many other organizations collectively together that we open source MONAI, which is a comprehensive medical imaging AI framework for leading organizations across the globe. On the left-hand side, you see that we built MONAI Zoom, MONAI Label, and MONAI Core for the model development. And on the right-hand side, you see MONAI Deploy, where you can get connected into cloud services and medical devices to be able to deploy at the hospitals near patient bedside. MONAI has actually been going on for quite some time. A lot of people perhaps don't know about it. For the developers that know about it, you will see that you are among the 650,000 downloads of MONAI, 50,000 downloads per month. There's 450 GitHub projects going on, 160 papers being published, and in fact, leading 30 medical centers are all using MONAI, and the 11 challenges won throughout. Since 2019, it's beginning to now, you can see many of the breakthrough and key celebration points highlighted on the slides at the bottom here. What was announced yesterday is that MONAI is actually now part of NVIDIA AI Enterprise. What's exciting about this is it's not just an open source ecosystem anymore. We start seeing hospitals using MONAI for enterprise deployment. And of course, the first thing is what happens if things don't work? We should have a number to call. So we, after hearing a lot of requests from the ecosystem, we decided to put MONAI Enterprise package together. This way, it's the most optimized AI workflows that can be deployed on multi-cloud or hybrid approach. And it's very secure, scalable, and it is mission critical support. You have a phone number to call if something doesn't go down, it doesn't work out well. And an open source framework is now being supported with large organizations like NVIDIA as well. This already been deployed across, adopted by the ecosystem, either from AMC enterprises to hyperscale integrators to clinical deployment platforms, you name it. These are just a few of the organizations that we listed, but there's definitely many more here. Looking at specifically who are using them, from surgeons to radiologists to hospital system integrators worldwide, they are sharing with us that MONAI can take them from years to days, be able to gain insights. Dr. Matthew Jolly has shared that with us. And MONAI can also scale across the entire medical records and patient pathway, where Harris, our medical physicist from Gates and St. Thomas, shared with us. The last on the right-hand side, George actually shared with us that MONAI is also acting as a healthcare OS that will be able to integrate every hospital around the world. And this is a contribution of many organizations, as you can see, like Harvard, Stanford, Mayo, National Cancer Institute, and us, Johns Hopkins. It's a combined effort collectively together that we contribute back to the community, standardizing on top of PyTorch. So to kind of go under the hood just a little bit to share with you guys what is the key thesis behind MONAI. So MONAI solved 5 key workflows. The first one is AI-assisted annotation to be able to help you label data a lot more effectively. And we can also train 3D segmentation model, intelligent model selection, and also training. Federated learning is it's a relatively new approach, been around for the last 2-3 years. You can keep the data where it is in the clinics and train the centralized model, and you don't have to move the data to preserve patient privacy and only share the centralized model across the board. And that's also open source under NVIDIA Flare, part of MONAI offering as well. And the translating AI model into application, which is part of the MAPS offering, has been able to help build and package models into deployable application. And the final mile of deploying to hospital infrastructure, standardizing on top of end-to-end clinical workflow that has been going on as well. Now, one slide each of these boxes. AI-assisted annotation, you can reduce the cost of data labeling up to 75% with viewer-integrated active learning, image selection algorithm, and of course, human in the loop to ensure utmost accuracy. And training 3D model, segmentation model, you will be able to get right out of the box Jumpstart training platform. And you can, just with a few lines, 1 to 5 lines of code, you will be able to build a 3D model from scratch. And it's fully automated to be able to help prepare data sets, create and fine-tune models, and also display results right away. And the training time reduced from like weeks to days is also something that our user base is very much looking forward to. Federated learning, as I mentioned, keep data where it is, preserve patient privacy, share centralized model for organizations together. And in the Nature magazine last year, 80 authors combined together published the exam model, which is to be able to predict the oxygen need for COVID-19 patients by using the federated learning approach. And so this has definitely taken off. I have seen a lot of startups building these into their business model, working with AMC hospitals around the globe, especially targeting rare diseases. So federated learning helps a lot with interoperability and then be able to distribute a lot of multi-party collaboration and generalize a lot of the models as well. Translating AI models to application is very important. So in this process, you're able to leverage what's offered in MONAI to be able to accelerate the application development, leveraging MAPS, which is MONAI application package. You can do so with a few lines of code, less than 20 minutes. And this is a repeatable deployment pipeline. I know there's a lot of people saying that AI is still a buzzword, deployment is not quite there, but I do see startups getting deployed in thousands of hospitals. AI is being deployed. A lot of them is passive AI that's happening in the background that you don't hear about. MONAI, as a community effort, we end up also sharing that to ensure this repeatable pipeline is out there and help you also streamline some of the AI lifecycle as you can continue to as the AI continue to learn to become smarter. How do you adapt the model from years to weeks and be able to do so more effectively? Then the last mile, bringing research to clinical production, is extremely important. So at RSNA, which is the largest radiology conference that's been going on for 100-some years now, last week, we officially announced MAPS, which is also a community effort. You can map once and run everywhere. This MAP is the MONAI application package. It essentially help you streamline a lot of hospital operations and be able to bridge the research all the way to the clinic. So specific feature and functionality, I only will touch on at high level because I don't know how technical the audience is. I don't want to lose half of you guys. But for those who are developers in the audience here, feel free to follow along because a few of them is quite exciting. And then I'll go into pathology specifically as I promised. Development and deployment, right? Development on the left and deployment on the right-hand side. You see that there's like accelerated development, reproducible models, path to commercialization, And on the deployment side is we're building a foundation to be able to get the research community access into clinics to generate significant impact. This is an eye chart, but going from the bottom, remember kind of like the 4-layer cake a little bit, MONAI ecosystem also follow a lot of that too. At the bottom, there's a lot of the systems and then the system software that we standardize on top of PyTorch. And then there is a layer of the MONAI tools, the MONAI label, core, deploy, and the model zoo, and many of the different components to all of the apps, model zoo, label sample, etc. And next page, I'm going to go into the MONAI model zoo a little bit just to let you know what are some of the models available that you can take right out of the box. So from the modality perspective, we support CT, pathology, MRI, X-ray, and video. And the application, there's segmentation, detection, classification, registration, and also reconstruction. So MONAI label can help you annotate, right, across radiology, pathology, and endoscopy, and you can see the full stack here. And it supports 3D segmentation, pathology, and 2D segmentation in endoscopy. And the viewers integration, what viewers you care about, we listed here. And also MONAI label server makes application ready to deploy and serve as a service. The core component help you to be able to train more effectively. There is a very robust backward-forward compatibility. You can actually design quite a lot with this very flexible approach. Folks that have used it share that 15x faster performance just on training itself using MONAI Core. Now going into specific a little bit about pathology, right? So pathology, we are building a lot behind QSIM as an application framework, which is an accelerated loading of medical image. Literally a pip install QSIM, you will be able to get access to this by going to GitHub. And QSIM stands for CUDA, which is the computing layer, so it's short for Q, and then Clara is our the Clara application framework and image, right? So it's QSIM. And the complex stack here that you can see for those who are technical can probably geek out here. And on the right-hand side, we have all of the QSIM actually get folded into another open source initiative that's for analytics under the Rapids umbrella. The problem that we're trying to solve here is that pathology slides are so big, right? And when you do ingest, the image IO is clearly a bottleneck for all of those who are maybe working on this problem. And that's where we come into play of help solve that problem as one of the first few problems in the pathology space. As mentioned, the images tend to be like 100 or 1,000 times larger than traditional CT and MR images. And sometimes you can't even load it into the GPU memory. So you need very efficient IO. So we end up offering a lot of new pathology pipelines and increase faster training time and new data loading libraries as well. And for offering a lot of this smart cache and also AMP support in the training aspect. And what you can do is just search MONAI lesion detection in digital pathology, and you will be able to see all of these offerings. On the right-hand side, the yellow chart, QSIM compared to other open source initiative like OpenSlide is definitely a lot more effective. Another use case, which is the stain normalization in digital pathology. I put this blog here for anyone that want to read a little bit more about. You can also see that the CuPy option compared to the traditional NumPy, which is another open source initiative, is definitely a lot more performance gain as well for both of the software and hardware treatment that we provided. This is about a year ago now, but just to catch you up on kind of latest integration, latest work. This is the one of the digital pathology pipelines that we offer the lesion segmentation from the data all the way to building a skill to seeing the eventual insights. A whole slide's inference time originally would have taken 11 minutes down to like 13 seconds. A very exciting thing about the GPU memory, which is a limitation for pathologists to be able to get a lot of data onto the memory. We are coming out with a blog post that is help accelerating digital pathology workflow using QSIM and GPU direct storage. And what that is that a direct path between the storage and GPU memory. So on the right-hand side, here are specific graphs that you can see that with GPU direct storage, how we help accelerate whole slide imaging IO and image processing. In read, we see 11.8x, up to 11.8x faster. And for write, and depends on if it's like the unit 8 or the float 32, we see speed up as well. And read and write, we also see upwards of 1.62. So for those that are developers in this space, you can take advantage of some of the upcoming speed up that's definitely much needed in this IO bottleneck area. And of course, you can access it everywhere, either on-prem, in the cloud, or potentially in testing environments like Launchpad as well. Now, as I mentioned earlier, I do manage 1,800 healthcare AI startups. That is one of the largest segment of 12,000 startups that are in our Inception program, which is a startup program, a free program for startups to join. These startups that are in our program representing in AI, deep learning, AR, VR, gaming, networking, and graphics in 100-some countries, cumulative $90 billion in funding. Last year, we grew about 60% of the members in our Inception program. With the 1,900 healthcare AI startups, they are evenly distributed in North America, Europe, and Asia. And I am tracking more than 300 FDA and CE marked approved applications that are in our program. We help the startups to build with us, providing technical expertise, grow with us with VC funding that are in our VC Alliance, and scale with them with a lot of go-to-market efforts. To showcase that even just pathology, we have about 100, and here are just a few that have done some fantastic work with us. Pathology.ai, they created this studio. It's a do-it-yourself platform that helps pathologists to be able to create AI solution for cell detection, tissue segmentation, and object classification using a relatively small amount of data without much AI experts to be able to find insights specifically. You can see on the background how they do the labeling and detection specifically.
Renee, sorry to interrupt, but we're a little over time. So if you can wrap up soon, that would be great. Thank you so much.
That sounds good. PathAI is another solution that's a household name in the pathology space. One very unique one is actually Grundium. They're a suitcase-sized microscope for pathologists now. They have already deployed 1,000-some units. Scopio Lab is another one that's doing some cutting-edge blood smear analysis. And for those who may not know what this space is like, I'll play a quick video, and then this is the last slide that I have. Noel is based in Korea, so you can do BCM analysis by entering patient information, and once the sample is in, then you can actually do a lot of the image analysis on the device itself with blood smear or fixation, staining steps, to digital microscopy, and be able to identify what's to label all of the data and move them around accordingly if they are mislabeled. And then with one click of a button, you can actually also generate reports for end users to take a look at. So solutions like these, we have tons in the program. Startups, feel free to join us. If for those who are interested in MONAI, here is some additional resources, and happy to chat about any other trends during the Q&A section. Thank you.
Thank you so much for the interesting talk. Very, very insightful. And I think we already have some questions, like one question, so feel free to keep on sending us your questions with the Engage tab. Let's move to the next talk. We will hear from Professor John Long, who will talk to us about the molecular effectors of physical activity.
Okay. Hi, everybody. It's a pleasure for me to be here. I'm just going to share this. So I am by training, a PhD in biochemistry, and I run a lab here at Stanford. We study metabolism and health. We do not do any AI, although maybe some of you can enlighten me on some of this, because I think that there could be some possibilities here. I just don't have a background on it. So these are my disclosures. What I tell you about is something very unusual that maybe you have thought about, maybe you haven't thought about, but certainly you have done, which is exercise. And I'm going to tell you about our efforts to really understand what's happening when you exercise and why we care about that, and then the role for AI in sort of helping us in our basic science efforts here. So this is a video of a mouse on a treadmill. It turns out that you can buy treadmills for mice. They will run just fine on these treadmills. This is happening downstairs. And the reason that we have these mice on treadmills is because we're studying exercise. And there's sort of this general idea that exercise is just a panacea for everything, right? Exercise is good for you. Everyone should do it. This is something that you're taught starting from elementary school. Every morning, I mean, I'm on my elliptical going back and forth, wondering, doing my thing and wondering what's going on. So the CDC, of course, recommends that everyone should exercise at least a few times a week. The recommendation is something like 150 minutes per week. And they also recognize at that level that there's a lot of benefits to physical activity. There are immediate benefits such as reduced anxiety or improved sleep. And then, of course, there's long-term benefits. Becoming physically active or starting an exercise program can help you with weight control, can help you with reduction of, for example, cardiovascular disease, can help with reduction of dementia and other Alzheimer's diseases. And so with all of these benefits, and for something that's so ancient, right, physical activity, what our angle that we have been looking at this is that it's remarkable how little is known about the molecules and the molecular processes involved in physical activity. To give you a sense, for example, we know more about yeast than we understand about physical activity. And so there's been a real effort by my lab and others around the country to really understand the molecules of exercise. Now, there's also a particular reason why now in 2022, it seems reasonable to ask this question. And really that key insight is provided by technology advance, a particular type of technology called mass spectrometry. This is an analytical chemistry tool that allows you to analyze with very high sensitivity and very high resolution the chemical composition of essentially anything in the human body, our blood, our tissues, our skin, whatever. So my lab has taken this approach, and we've looked at exercise across a variety of different modalities in people. We can get kids that are exercising, seniors that are lifting weights. We can also look at exercise in non-human models such as horses, mice, and sled dogs. And we can use this mass spectrometry tool to try to understand what are the molecules that are changed with physical activity. When we did this experiment, to our surprise, what we found was that all of these organisms that move turn on the same molecule when they exercise. And that molecule is shown here. It's called LAC-Phe. The chemical structure is shown on the left, and sort of a 3D rendering of that chemical structure is shown on the right. For the aficionados in the room, you'll know that or recognize that we call this molecule LAC-Phe because it's 1/2 on the left side lactate, and then 1/2 on the right side, the amino acid phenylalanine. So it's a conjugate and a derivative of lactate. Now, it turns out in humans that the production of LAC-Phe always goes up in exercise, but different types of exercise will upregulate LAC-Phe to different amounts. And so if you are, for example, sprinting, this is a type of exercise that will induce LAC-Phe the most. And that sort of makes sense because when you're sprinting, you're actually producing a lot of lactate, right? So the more lactate you produce, the more LAC-Phe you produce. And then we can also see LAC-Phe inductions, but not so much, for example, under endurance exercise when the amount of lactate that you're producing is much less. And then resistance exercise, for example, squats or leg curls are somewhere in the middle. So is the production of LAC-Phe in exercise just a byproduct of physical activity, or is it something that is actually an effector of physical activity? And what we show is that it's actually the latter, and we think that LAC-Phe in part is responsible for why you don't feel hungry after a hard workout. So what got us on this track was the observation that the more LAC-Phe that you could make, the leaner you were. Okay, so shown in these two graphs is BMI, which is body mass index on the left, and then estimated fat mass on the right. And you can see there's a negative correlation between how much LAC-Phe you can produce and your body weight. And sure enough, if you take mice and you give them synthetic LAC-Phe that you can make in a lab, they will stop eating. Okay, and that's shown on the left. So these are mice that are given lac feed, and then when you're monitoring food intake over the next 12 hours, they eat about 50% less than mice that are not given lac feed. But they're otherwise doing fine. For example, shown on the right, you can see that they're moving just fine. Okay, so this is a specific effect on the suppression of feeding. We can also engineer mice that, for example, cannot produce lac feed after exercise. And what happens in these mice, because they can't turn on this appetite suppressing factor after exercise, is that they eat more and they get fat. So on the left is the data on the food intake, on the right is their data on the body weight. And what we were able to subsequently show after we saw this was that lac feed actually acts in a part of your brain called the hypothalamus, which is known to have populations of neurons that regulate your food intake and appetite. So these are called orexigenic or anorexigenic neurons. And we could show using various techniques that lac feed is really acting on this part of the brain to control feeding behaviors. So this is the pathway that we have discovered, which is that under conditions of exercise, when you're exercising, you produce a lot of lactate from your muscles. That lactate is then converted to lac feed, and I didn't really talk about this part, but it's mediated by a certain cell type that's marked by a gene called CNDP2. And then lac feed goes to your brain to suppress feeding and obesity. Okay, so that's the biochemistry and the physiology of my talk. So here comes my naivety about AI and maybe ways that AI could help us here. So you could reasonably ask in sort of what I told you here, well, why did it take until now in 2022 for my group to discover lac feed and to dissect exercise in this way? And why wasn't this discovered, whatever, 10 years earlier, let's say, right? And as I mentioned, part of the effort, sort of the impetus for launching all these efforts to try to understand the molecules of exercise is that there's recent advances in mass spectrometry technology that allow us to look more deeply and with higher sensitivity at the chemical composition of any biological specimen. What I didn't tell you was that when you actually look with these instruments, most of what you see is complicated and poorly studied. Okay, so what I'm showing you here is a representative mass spectrometry trace. You don't really need to know anything about it, but to say that every time you see a peak that's given a number, those are molecules that we know about. And then every time there's a peak that's in a gray region, which is like half of this graph, those are molecules that we can detect that we know nothing about, okay? So for instance, if you look at the set of molecules regulated by exercise, we don't actually know what the chemical composition of these molecules are. All we have are these molecular formulas. And what we've done, and in the work I've shown you, is we've just taken, the top hit out of this, and we've characterized it to be lac feed, and we've worked out this entire pathway by which lac feed is mediating exercise-inducible regulation of appetite. But of course, there remain many possibilities for sort of high throughput AI-driven approaches to start to do this in a more systematic and rigorous way and try to uncover more molecules of physical activity. Of course, in the long term, the goal of all of these efforts would be that by understanding these molecules, you might be able to therapeutically harness exercise and augment it, especially in cases where, for example, the elderly maybe cannot exercise to the intensity that they would need to see some of the benefits. And so we could provide some pharmacological and therapeutic assistance there in the form of medicines. Okay, so just to wrap up, what I've told you about is how exercise induces the production of a molecule called lac feed, which suppresses feeding and obesity. There are probably many additional exercise-regulated molecules and interesting pathways that remain to be discovered. And maybe AI can be useful for combing through the mountains of data that we're generating with mass spectrometry to try to identify what they are and also to figure out what they do. Okay, so I'll close with that. This is my lab. You can follow us on Twitter at LongLab Stanford. And I'm happy to take any other questions at the end of the section. Thank you.
Thank you so much, John. Very, very interesting. Now let's move on to our last presentation for this session by Sana Deli, who will talk to us about the digital biomarkers at the age of AI for disease diagnosis. So, Ihsan, the floor is yours.
Amazing, thank you. You hear me fine, right?
Yes, we hear you and see you and
see the full screen.
Slides. Yes.
Great. All right. Yeah. So, hi everybody. I'm excited to talk to you today about digital biomarkers at the age of AI for disease diagnostics. Okay, let me first start by defining biomarkers. A biomarker is a biological marker. A biomarker or a biological marker is a broad term for something we can test or measure to confirm presence or absence of a disease or risks of a disease. There are two broad categories of biomarkers: imaging biomarkers that are things we can often see, like tumors that show up on an X-ray or on somebody's lung, for example, and molecular biomarkers, which are types of measurements that include any type of molecule that can be taken from someone, for example, from the blood or from biopsies. So what are digital biomarkers? Digital biomarkers, a newer term these days being used a lot. They are defined as objective, quantifiable, physiological, and behavioral data that are collected and measured by means of digital devices such as portables, wearables, implantables, or digestibles. The data collected are typically used to explain, influence, and or predict health-related outcomes. As an example, the Gen5 project at the University College London presented the current status of digital health technology development within the Genetic FTD initiative, or Gen5, a European-Canadian natural history study of frontotemporal dementia, or FTD. Gen5 has done extensive work tracking behavioral, cognitive, language, neuroimaging, and fluid biomarkers in its cohorts. Now these tests are being deployed in digital form using smartphones and tablets and devices like Fitbits. There are two different types of digital biomarkers: passive and active. Passive biomarkers are collected via unnoticed interactions. For example, heart rate, oxygen saturation level, speech sentiment, smartphone usage, location, and so on. While active biomarkers are collected via active interaction in a task, for example, on a mobile phone or a tablet. For instance, inertial sensor measurements when prompted to walk in a straight line, measuring gait, smart device measurements when tapping, swiping, and typing, and smart device camera measurements of eye movement and facial expressions. It is known that aggregating both types of active and passive cognitive sources yields a better understanding of disease characterization in many cases. From a different perspective, looking at types of digital biomarkers, first let's see how traditional biomarkers were categorized. Traditional biomarkers are divided into 7 broad categories depending on the clinical goal of the biomarker, such as safety, predictive, diagnostic, etc. All 7 categories are shown here on the right. Digital technologies enable the measurement of digital biomarkers, which contribute new and unique features, for instance, longitudinal continuous measurements and so on, while sharing the same traditional biomarker clinical goals. There are a lot of unique opportunities with digital biomarkers. For instance, they have shown success in early diagnosis of health conditions and timely treatment for continuous monitoring. They could be used for personalized preventive care tailored to patients' features and specific behaviors. There are a lot of technologies out there right now that can be used, such as smartphones, fitness trackers, and so on. They can increase efficiency in clinical trials, since they can remotely gather and analyze data for, say, drug trials. Furthermore, they can use patient analytics to improve adherence and patient engagement. They can be used for effective disease management, since they are efficient for both individual and population level detection, for example, for COVID-19 tracing. They can help with risk evaluation or management of risk of like disease progression, comorbidities, and detecting individuals at risk. They can be also crucial for detecting and tracking mental health conditions and trigger early intervention to prevent adverse outcomes. Another avenue of their developments is AI-driven methods for measuring digital biomarkers. However, in the current literature, AI is often used for pre-processing, feature selection or engineering, and analysis of digital biomarkers. We argue that AI can also be used for automating digital biomarker discovery and generation. AI allows for enhanced precision in creating panels of actionable biomarkers, enables rapid assessment, and facilitates preventive measures. For example, AI-powered digital biomarker discovery for P4 medicine or predictive, preventative, personalized, and participatory, the P4 medicine. Each of these steps can use AI for automating disease discovery, diagnosis, decision-making, and intervention. For the sake of time, I don't go deeper into this, but I want to provide you with an example. Let me start talking about our recent work. For the first time, we proposed a computer vision-based model that estimated motor impairments severity using only video. We did so by first extracting the 3D human or skeleton data from the videos. This greatly reduced the dimensionality of the data, was efficient in the required number of samples, and anonymized the data. Only the skeleton was used to estimate the gait score based on the MDS-UPDRS, which is Movement Disorder Society Unified Parkinson's Disease Rating Scale. Therefore, our method was entirely vision-based, used non-intrusive video recordings, and was scalable because all we needed was a video of patients walking. Our results showed that our AI algorithms were able to achieve reasonable performance across all classes of motor impairment severity. Our method sets a new benchmark for this task with a macro average AUC of 0.90 and balanced accuracy or average recall of 81%. The confusion matrix of predicted versus ground truth classes also showed that our method did best on class 0 and 1, followed by class 3 and then class 2. Clinical context suggests our results are consistent with physician experiences. The top 4 body joints are visualized here using these green circles together with the average motion for each score. They serve as computer vision and AI-driven digital biomarkers for estimating Parkinson's disease gait impairments. In these visualizations, we can see the classes 0 to 2 progressively decrease in mobility with reduced arm swing and range of pedal motion, reduced stride amplitude and foot lift, while class 3 becomes imbalanced. Just to clarify, these points that you see here are the ones that those joints contributed the most in predicting the gait scores, the gait impairment severity scores accurately. Even when there is uncertainty and different clinical raters rates same patient differently, our method consistently rates the participants and conforming with the majority votes. Our method rates the participants' gait exam within the range of actual physician ratings 87% of the time. This demonstrated that most of our model predictions can be considered acceptable scores. We also showed if we train our model with even fewer data than we have, we still obtain strong results. We sample either 25%, 50%, or 75% of the data for training. We find that our model, our very recent proposed model named Gateformer here, maintains relatively strong performance with only a fraction of the data. With access to 25% training data, it achieves an F1 score of 0.56, which is higher than a state-of-the-art prior method SDGCN, using 100% of the training data, and is comparable to our previous work, the dotted line, using all of the data, 100% of the data. These results show the power of our summary digital biomarkers for even few shot gait impairment severity estimation. Let me show you an example of how we process the data. You can see the original video with the overlaid 3D mesh and body skeleton on the left, and the side view is in the middle. This shows how our model is able to accurately extract a 3D model of the human motion only based on a video, like for example, an iPad video. On the right, you can also see some detailed stats about the walking sequence, including the knee angle over time in the top and feet contacts with the ground plane in the bottom. With this detailed analysis, we can extract all the relevant information for the full walking cycle. Especially, we extract more interpretable variables only based on the video, including walking time, walking or gait speed, double support time, average dorsal inclination angle, and so on. We have explored the interpretation and correlation of these variables with respect to frailty instruments as well, which show clear signals in the AI-driven process data for predicting frailty of individuals. Okay, to conclude and summarize, I want to draw your attention to these 2 points. Novel computer vision and contactless sensor technology create a great opportunity to identify innovative biomarkers that can be measured frequently and longitudinally. AI can help automating digital biomarker discovery and generation, potentially leading to breakthroughs in disease diagnosis and tracking. At the end, I would like to thank all of the amazing collaborators and the students who are listed here, are the ones I have presented some of their work. And thank you for listening, and thanks for these. Thanks to these institutes for supporting my research as well.
Thank you so much, Iksan, for your great talk. So I think now we can move on to the panel discussion. We already have received many interesting questions in Slido, so I would welcome all other participants who would like to ask a question to head over there and type in their answer, or rather their question, excuse me. So maybe we can start with a question. I'd like to point to Sharmila and Iksan, and you can answer it both in order, which is, how do you envision the digital biomarkers standing on their own or being combined with biomedical or other biomarkers to provide clinical care utility? Specifically for Sharmila, in your case, you showed us that you're using the MRIs and the X-rays, but then you also have the clinical data like the demographics and the other information like BMI. So do you combine these? Do you see these things used separately? How do you see this direction?
The way I see it, I know it's a complicated problem, but I think it is a combination of imaging as well as the the clinical demographic data, as well as combining, for example, the digital biomarkers, which will potentially give you information about gait, imbalance, asymmetry, and so on. I think it will all end up answering a lot of questions, because the body, for example, since we are talking about skeletal movement in this particular case, does not work basically in a singular manner. Everything works and functions in unison, and as imaging metrics are manifested in some of the performance and the gait metrics. So I certainly think combining electronic medical health records, even geospatial data, for example, and along with some of this biomarker, digital biomarker data, imaging biomarker data, is what makes it so exciting right now.
Absolutely, and I couldn't agree more, because generally the field of digital biomarkers being a newer field and still being explored, most of the markers that we often are able to extract and identify are very good pointers for giving us predictions of risks through time, while the traditional biomarkers are more or less more reliable in terms, because they are measuring the blood, or like, for example, they are measuring the molecules directly. So with that in mind, I definitely think that these digital assessments, because they are cheaper and faster and more frequently could be capturing data, are very good for at home or remote monitoring of the disease and risks of disease, and paired with some other factors, including EHRs, they could be very useful for making informed decision and making the actual diagnosis.
Yeah, very interesting. I think since Iksan, we heard your question, your talk last, maybe I have a specific question for you from Wenwen Zhang. The question is, does the data come from one person? Will gender and age affect the result of gait former?
Very good question, very specific and targeted question. Yes, so the thing is that that's very good question. The thing is, age and many other factors, they not only affect the model that we trained, the age and sex in general, they affect the model and its outcomes, but it's also the same for almost all of the other models. What we often do is we consider these types of demographic information within the model, or they consider them as some sorts of confounders, so that we understand that we need to model the effect of these specific variables as well, because we know that age and sex are directly affecting how people walk. So and that's a very important factor. One thing that I wanted to mention is specifically because you asked about the gait former model. I didn't go into the details, but in order to build that model, what we did was we gathered a lot of human walking and activity data sets out there in public. We use them to pre-train a model called Gateformer that generates some motion representations. And then based on those motion representations, we try to predict gait severity scores. Since that data was a huge data set, combination of different data sets, we have hoped that the effects of things like age and sex were less pronounced in the motion representation, and we could get the factors that are actually about the motion itself and not reflecting the other variables.
Thank you very much. We have a question for Renee, which is how does the NVIDIA startup program compare to other accelerators or incubators, for example, in regards to funding, cross-collaboration, etc.?
NVIDIA Inception is free, first of all. A lot of the differences, I think, compared to others is that we focus on technology integration. Let's say that if you as a developer or startup want to use any of the SDKs that we listed out there for free, we will come in and help you with optimization and support if you run into issues. And we also have VC Alliance that I briefly mentioned, which has 200 to 300 VCs that are in the pipe that will get access by the members in the portal, and they can actually raise their hand essentially to get connected in the portal directly about the round of funding and the segments that they're in. And of course, there's a go-to-market support. We not like other incubators, there's no deadline or cohort. You can join anytime. You could be two people in a garage or about to go IPO. We will only reject you if you, for example, either or remove you from the program if you're end of life or got acquired or turned IPO, then you become an alum member of the Inception program. There's tons of benefits that are free for the startup, so we really look forward to seeing you in our community. About venture, besides like VC Alliance that I mentioned, it's a dedicated program for external VCs. We do have 2 internal VCs inside of our NVIDIA corporate. One is GPU venture that's strategically aligned to our business unit's priorities. And the second one is N venture that's more financial return based. So if anyone wants to ask more questions about the details of the programs or other technical questions about solution developer toolkits, I'm happy to connect you with on LinkedIn.
I think that's a great gateway to the next question that was also for you, Renee, which was if someone is looking to get into this field and looks for mentorship, where is this available if it's not available within their own organization?
Getting started, I highly recommend Deep Learning Institute. NVIDIA built together curriculums that are like over 100 some Deep Learning Institute curriculum. If that's not something that you didn't find something that you're looking for, of course, Coursera, Udemy, even like Stanford Continuous Studies are all really good ways that there's like actually classes that you can take to get started. In terms of mentorship, we don't directly have mentorship program within the startup program, but of course, individual outreach depends on what you're looking for. If it's a good fit for both people, I think there's definitely mentorship that could be worked on, and that mentorship means a lot of things to a lot of people. So that was probably a separate conversation.
Very, very interesting. I think there are a lot of opportunities and a lot of resources out there nowadays for deep learning, and Mon AI things become much simpler. Maybe John, I have a question for you, which is you presented this very interesting problem with or this interesting finding with LAC-V. What kind? I'm not an expert at all in this field, so as a person, like as a deep learning person, what kind of biomarker? So like, what kind of data would one analyze, and what do you have data that are available? Like when you would start a collaboration with a deep learning side, like what would be available for them?
Yeah, I think so. There's a lot of both public as well as sort of pots of mass spectrometry data all over. Okay, and I think there's a real gap here because the upward trend of mass spectrometry is just like totally nuts. You got metabolomics, lipidomics, proteomics, all this kind of stuff, huge amounts of data. the large majority of it, greater than 90%, is discarded because of this annotation problem. So you have basic scientists like me that are looking at this data. We can figure out what we can figure out, and then there's just huge piles of it that are just sitting there. And there have been some efforts to, for example, do some training on that based on known compounds, and to try to, use larger scale AI approaches to annotate that large data set. And people like me would love it if people who knew how to do this would actually come in and do it. So I'd say as far as the data sets, there's some public repositories, there's Proteome Exchange, there's the Metabolome Workbench, other things like that, where you can just download all the data from there.
This is very, very interesting. And here at Stanford, do you also do you do studies on volunteers or on humans, or do you focus on the mice and the horses?
Well, we do some human studies, but those are typically in collaboration with others. So, for instance, there are clinicians here at Stanford Medicine that are running trials. Blood, for example, is one of the most commonly sampled biofluids ever in the hospital setting. And so that typically becomes sort of our sample of choice when we're doing these large-scale mass spec experiments.
Thank you very much. We have one more question. It's Slido. And again, I would like to encourage the audience to ask more if they have to. We have another around 10 to 12 minutes of discussion, so please feel free to ask your questions. This question is for Ehsan. So it is, if the data from the biomarkers that you're collecting are noisy, what do you do to process that noise?
So this is, first, it depends on what type of biomarker we're talking about. So if it's about traditional biomarkers and detecting, collecting the data with devices and with medical devices, medical tools, yes, always there is the chance that there's some either missing data in data sets or noise present in the data. With respect to the digital biomarkers, it's almost the same story, because either AI is being used to extract that biomarker or measure that biomarker, and we all know that AI itself is never 100% accurate. So there is probably noise there, and also for the cases that they are using some sensors, for example, the wearable sensors, or like Fitbit or like rings, they also come with noisy measurements, because those sensors require specific conditions or sometimes a touch on the skin to be able to measure the biomarker. So there is always this risk of noise. And in order to mitigate this on the method side, on the technology side, we often rely on methods like robust regression, or methods for identifying and removing noisy data or compensating for them, which in machine learning, we do have a lot of such models and methods. And as I mentioned, one of the simplest ones is robust regression. Other types are for example, random sampling type of methods. Landsat is another kind of method that could be used for these purposes. If you are building multivariate models, I'm not sure if this answers the question, but my short response was basically working a little bit on the measurement side to improve the measurement noises, and on the method side to basically identify and fix the noisy parameters.
Thank you, Ehsan. I have a question for Sharmila. I really liked the fact that you always included the radiologist in the talk. So you wanted to see kind of compare how the trainee with the more experienced, and how AI helped trainee. So how did you find was the best way to kind of present the results to the trainee to help them for this task of like identifying the regions or improving their annotation? So was it like a report, or was it some sort of uncertainty map or visualization? So what was the best solution you found?
So I think the way we finally settled on it was to provide a report, which basically was color-coded, like I showed you, because there's a whole lot of output that comes out of any AI algorithm, much more than they want to see. And sometimes every little dot gets highlighted and the radiologists say, please do not show me that. So I think the color-coded map that I showed was really useful, but we also provide on that color-coded map, some of the radiologists wanted probabilities. The problem that we face is, with the trainees, if we tell that if there are 2 trainees and we're working with radiologists, then the output is really what they want is guided by the radiologist's desire, and the trainees fall into place. But no 2 radiologists actually agree on a particular way of presentation. People often like the saliency maps, but those are very variable. Sometimes, it becomes difficult for people to interpret those, and there's issues associated with interpreting the saliency maps. So I think we have to be a little bit careful along those lines. And I don't say we have a solution. We are sort of tailor-making the solution based on the body part and the radiologists we are working with right now. The way I see it for industry is to provide several ways of doing it, so every radiologist can pre-format the report for a template that they like. I think that would be the way. I know it seems like a overkill, but nobody's going to agree on anything. Trying to get any 2 radiologists to come to consensus is very hard.
Absolutely, makes a lot of sense. I've also experienced the difficulty of bridging this gap between
it's very difficult.
The model language and the radiology language is always hard to bridge. We have another question of the audience, which is, what is the best approach for using AI for neuroimaging data coming from the clinic? Research grade and clinical grade imaging are sometimes not compatible.
Exactly.
So, what do you think about that?
It is absolutely. There's domain adaptation, which you can start working with and trying to look at clinical data. The problem is the research data is far more curated. It sticks to a protocol. It is all the imaging fields of view and all the other parameters are often kept fixed unless there's a particular site that doesn't follow protocol. But most of the time, it is far cleaner data to actually get research data that is collected. Clinical data varies depending on the disease, the interpretation. Sometimes there's missing data, missing sequences. So I think that is really an issue. I think that as we develop the biomarkers, possibly in research databases, we will have to see whether we can extract the same biomarkers with missing data, with noisier data, with less stringent data, retrain models, maybe have continuous learning models and others. But that data is an issue. And sometimes images from 2 different scanners, even following the same protocol, have issues associated with it. And I think domain adaptation will be a big deal in terms of generalizability of some of these models, I think. It is a complex problem, but
Absolutely. And I think maybe also NVIDIA and how the MonAI collects the data from different hospitals, like with the federated learning approaches, maybe will help domain adaptation more, because we'll have more access to even more data to kind of be able to have more generalizable algorithms, hopefully.
I think one thing to caveat there is NVIDIA is a technology company, right? And for us, we actually don't hold on to the data in any way unless NIH or other organizations have strict legal restriction about this data is de-identified, it's only used for this project, for this purpose only, and for this duration. It's very, very strict. And then when we do decide to go into some sort of a joint research agreement, the end result, let's say if it's a model, if it's going to get published out there, those are all written in very fine line. And then how will the B model be used for research or deployment purposes? It's all very much like written down. So the federated learning approach in particularly actually is to not move the data. but build the centralized model, and you share weights of the model. So that is a very unique approach to ensure data stay where it is.
Exactly. No, I think that's a very good point. Maybe I have in my mind more like academic collaborations where we kind of work with other institutions and data flow more freely than with the industry. Absolutely. We have one more question for Ihsan, which is, do you kind of feel like in the future for the GATE project, more wearable information coming from wearable sensors will replace vision-based data?
That's an interesting question. I'm thinking that it's going to be the other direction, because wearables and these types of sensors, they are often I don't want to use the word intrusive, but they need to have like active engagement with the person, with the patient or the individual. They have to have it on. They should be always like charged. Otherwise, they're not going to be of any use. As opposed to vision-based methods, they often come with contactless sensing, getting the data without any involvement or engagement of the individual, and processing it completely seamless from the individual's perspective. And this is probably going to be of greater use in the future, although vision-based methods are rather, so to say, harder to implement. That the research is still, the methods are not completely developed, while variables will give us like very simple and raw measurements that could be that are ready for being processed. So basically, I think that it is going to be in the future use of more contactless type of sensors rather than specifically wearables.
Thank you very much. And I have one last question in general for the panel, which is some folks viewing the session work in high tech. What tools or other support might be helpful in advancing your research? How can industry members help? I know Renee gave us, of course, a lot of information about NVIDIA is helping research, but in general, from the more the academics in the panel, besides NVIDIA, what else? Like, how else would you collaborate with research, with industry? Excuse me.
I can actually share a few more. I didn't touch on too much of the research side. I touched on startups. I touch on resources for you to advance if you want to learn about AI and deep learning. If you are an individual developer, there is the NVIDIA developer program. You can register as an individual. There's a lot of product as an individual you can actually use for free. And then on top, we consider them as developers. The biggest developer conference that are free, we host like twice a year. A lot of latest AI stuff is in our GTC, GPU Technology Conference. Next one's going to come up in March, virtual again as well. And then if you're a researcher, there's also a research program as well that you can apply. There's lots of benefit for you as a researcher. And if you're a research within the university, there's specific benefits for you too. So ensure that you select the right category. And of course, as researcher, there's always collaboration that we do with industry, like we jointly write papers together. Those are all opportunities. I think the best approach is that if you know someone at NVIDIA, if you know based on the 4-layer cake that I share, you can tell that this is a strategic direction that NVIDIA is going in, then writing a joint paper together that somehow fits into your thesis, then it could be a very good way to collaborate. So I just want to round up that answer and I'll pass it to the other panelists.
Thank you. I think we really have, I think that at 1:30 our session will be cut because of time, but we have one last question for John. So if we can give a very fast answer. Does timing of exercise, early versus late, affect production level of Phi, knowing the variation in daily circadian rhythm?
No, anytime. Just the harder you go, the more you get.
Oh, you mentioned also different types of exercise. So it's like more.
Sprinting is the best. So we did the best is like if you're running stadium stairs, the more anaerobic work, the more lactate you can push yourself, the more lactate you'll get. I would also suggest, by the way, that for appetite control, you should not be taking, for example, slow walks around the block, right? That there are other counter-regulatory appetite hormones that kick in during that might, for example, stimulate feeding. But what you should really do for appetite control is really in like high intensity interval training, HIIT training, right?
That is excellent information, and thank you all for participating. Thank you for your wonderful talks and very interesting discussions. Let's keep in touch. We have now that you know our panelists, you can stay in touch with us for further questions and with me. And yeah, have a great rest of your session in the conference.
Great, thank you.
Thank you.
Thank you. Great meeting you.
Thank you so much.
Good seeing you.